Here's another problem from chapter 5, and here we're looking at Friedelcrafts acylation, and this is an intramolecular type example. So take a simpler example for comparison. Let's say we had something like this, benzene ring, and let's say there's a methyl group here. If we go to acylate toluene, this is an ortho-para director. We would use AlCl3 for our catalyst. What that would do is connect this to the ring where the chlorine is attached to the carbonyl. Now that carbonyl carbon is bonded to the ring. So this, of course, the other product is HCl. So what we're going to do is make a connection from here to the ring, but this is an alkyl group here. Just like a methyl group, it's an OP, ortho-para director. So it can go here, or it can go here. I showed for this other example para, but it could also go ortho. So this connection is going to go to here or to here. What you find is that 5 or 6 membered rings are favored. They form very easily. So if we put it in the ortho position, that will form a 5 or 6 membered ring. If we go to the para, it's going to be a little too far away. It's going to be very strained if we try to do that. So we have 1, 2, 3, 4, 5, 6. If you make the connection at the ortho and come back around, what we're going to do is have 1, 2, 3, 4. That's where our carbonyl is. And then here is the new bond right there. That's our new bond that we formed. So that is an intramolecular Friedelcrafts acylation. Now, in this problem, number 52, it says that these syntheses have some flaws, and you're supposed to find out what's wrong with them. So, in the first step, we are adding chlorine. So let's work on A here. And it appears that the chlorine has been added. And then the KMNO4 oxidizes. So the methyl becomes the carboxylic acid, as we've talked about in this chapter. Alkyl groups on the ring will oxidize in that way. But where is the problem in the synthesis? Well, the CH3 is an ortho-para director, but Cl is meta. So that can't be right. What you could do instead is the oxidation first. Let's do the oxidation first. So here's our ring. And we have our methyl group. And if we did the KMNO4, we would get a carboxylic acid. Now this is a meta director. So now if we add the chlorine, it's going to add it in the meta position. So that was the problem with that one. Now for B, we are adding an alkyl group, and chlorine is an ortho-para director. So that looks like it was added para, and that works out well, but the problem is actually here. When we go to oxidize, we need a hydrogen on the carbon. So for instance, after we've added our group there, we'll have this CH3, CH3. It's a tertiary butyl group, but the carbon that's on the ring has no hydrogen, so you cannot oxidize that. So there's the problem with that one. So I like these problems because they take ideas that you've seen and go a little outside the box and make you think a little bit. We have something like a Friedelcrafts acylation here. We're putting alkyl groups on an aromatic ring, but we don't have our Lewis acid catalyst. We don't have AlCl3, but we do have an alkene here with some acid, and we've seen something like this before when we did alkene additions. We can protonate the alkene like we did when we did hydration, for instance, of alkenes. It puts a positive charge on this carbon. And why did I put the hydrogen there and not on the other carbon? Because in this case, I get a tertiary carbocation. If I put the hydrogen on the other carbon, we would have a primary carbocation. Well, this is a great electrophile because it has a positive charge. So now I can take my aromatic ring and I will have to show the hydrogen now, just the positive charge. I can have this reach out and I get the beginnings of an electrophilic aromatic substitution reaction. And in this case, it would go here and the positive charge would be there. And then it would follow the next step in electrophilic aromatic substitution is to remove the hydrogen from this location and reestablish the aromatic ring. So why does it go there? Because this is the stronger activator, and it's an OP director. It's a stronger activator than a methyl group, so it controls where it goes. The para position is already taken up by the methyl group. Finally, what we call a roadmap, a sequence of reactions. You're kind of putting together everything you've learned. So for step A, how do you put that group on? What reagents would you use? Well, that is a Friedelcrafts acylation. So you use the alkyl halide and aluminum chloride. And then for step B, we are doing bromination. So you use bromine, and you could use aluminum bromide or ferric bromide. For step C, what are we doing there? We're doing oxidation. This is oxidation of this chain here. So KMNO4. Usually there's acid, but a lot of times that gets left off, but probably should say H plus also. And then finally, step D, we are sulfonating the ring. And so that's going to be H2SO4 and sulfur trioxide, fuming sulfuric acid.